Hello everybody. আমার কথা শোনা যাচ্ছে? Hello, am I
Yes,
audible?
sir. Yes,
Okay,
sir.
okay, thank you. এখানে দেখা যাচ্ছে জ্যোতির্ময় নূপুর।
Yes, sir.
You raised your hands. Do you have any question? নেই। ওকে, তো একটা ইনফরমেশন আমি তোমাদের দিয়ে রাখি, দ্যাট এই যে ক্লাসটা করানো হচ্ছে এই ক্লাসটা রেকর্ড করা হচ্ছে এবং পুরো রেকর্ডিংটা ক্লাস কমপ্লিট হয়ে যাওয়ার পরে ইউটিউবে দিয়ে দেওয়া হবে। তো সবার ইনফরমেশনের জন্য এটা জানিয়ে রাখলাম। তো আমি শুরু করছি আজকের এই ক্লাসটা। আগের দিন আমরা ডিফারেনশিয়াল ক্যালকুলাস তার মধ্যে যে ডেরিভেটিভ ডিফারেন্সিয়েশন এটা নিয়ে ডিসকাস করেছিলাম। তো আজকে আমরা যেটা নিয়ে স্টার্ট করব দ্যাট ইজ অ্যাবাউট মিন ভ্যালু থিওরেম। তো আগের দিন যা কিছু পড়ানো হয়েছিল ডিফারেন্সিয়েশন চ্যাপ্টারটা থেকে, সেখান থেকে কারোর কোনো কোশ্চেন আছে? কোনো জায়গা থেকে কোনো কোশ্চেন? এনিবডি? নেই? সো আমি তাহলে ধরে নিচ্ছি চ্যাপ্টারটা মোটামুটি কমপ্লিট, বিকজ এখানে আর বিশেষ কিছু নেই।
सर
हाँ, यस।
हिंदी में बोलिए ना सर, समझ में नहीं आ रहा है।
Okay, do you have any question from that portion in the chapter? In fact, I am not familiar with Hindi. I can speak better in English.
Okay, sir.
So do you have any question from that portion that
No,
I
sir.
did in the last class? No one.
No, sir.
Okay, so I hope everything is clear to everybody regarding that differentiation portion. Now today I am going to start another chapter that is called mean value theorem. Let me first show you the modified syllabus from which I am going to discuss, because this would make your idea clear. So let me open this modified syllabus, just a minute. Over here, and let me share the screen so that you can all see this portion. Where is this? Yeah, this one. I'm going to present the screen. Now, is it visible to you all on my screen?
Yes, sir.
Okay. Now, as per the modified syllabus, this is the paper that I am going through, and I have completed this portion, differentiation of a function, algebra of differentiable functions, and all this portion that I have completed. Next, I am going to start this portion, Rolle's theorem, mean value theorem, etc. And this portion, the remaining portion, the relative extrema, interior and extremum, interior extreme theorem and all, and that I shall discuss later after completing this portion, this chapter, that is the chapter of mean value theorem. Now, this part, Rolle's theorem from this chapter. This actually, the chapter is in the book of Hoshan Maiti. It is included as the chapter of mean value theorem. Everything is there: Rolle's theorem, mean value theorem, then Cauchy's mean value theorem, etc. And this intermediate value property of derivative has been discussed as the statement, but I have something doubt regarding this truncated portion, because this is actually included in the differentiation chapter, although only the intermediate value property of derivative has been included over here, but I think that the total statement along with the proof should be included. So if I get any more extra time after completing this portion, I will go through the remaining portion that I just went through, that the statements only. I would like to go through the proof of this type of result, because intermediate value property requires the proof of Wester's theorem and all. So I will again come back to the chapter of differentiation that I left only the proofs, and I just went through the statements. Hmm. So let me start with Rolle's theorem. This Rolle's theorem in the chapter of chapter 11, probably the chapter of mean value theorem. Hmm. What I yeah, this is the chapter of mean value theorem. This is my written, my handwritten portion, not handwritten type portion. Hmm. Over here, I will have to go through mainly at initial stage. I will have to go through three different kind of theorems. One is this theorem that is called the Rolle's theorem. Second one is, this is called the mean value theorem. Hmm. This is the mean value theorem. And the third one, so somebody calls it called Lagrange's mean value theorem. And the third one is called the Cauchy's mean value theorem. So we'll have to discuss mainly three theorems, and one more theorem should be discussed at the end of this chapter, that is called Taylor's theorem. So altogether, the chapter is about all these four theorems. Hmm. And each and every such theorem has three different versions. Got it? So apparently it might look that we have 3 into 4, altogether 12 theorems, but basically it is about four different results. The first result is the result that is called Rolle's theorem, that I am going to discuss over here. Hmm. The Rolle's theorem. Let me open another file. It would be helpful for me to discuss from that file. This is the file. Hmm. So this is the first theorem that I am going to discuss, is this Rolle's theorem. Got it? Over here, this Rolle's theorem says that probably you have gone through this the same kind of theorem in algebra in the chapter probably theory of equations, I suppose, or in the chapter of polynomials. Hmm. Anyway, so this is actually the general version of that general proof of that theorem, general version. Over here, the function f has mainly three properties. First of all, it should be continuous in certain open interval ab. Okay, and in that proof of algebra, the function f was chosen as a polynomial function. But we know that polynomial function is a continuous function. But apart from polynomial functions, there are other continuous functions as well. So over here, we are considering a function f defined on a closed interval ab and satisfying three properties. First, the property is that the function is continuous in the closed interval ab, and the second property is that the derivative f dash, this derivative exists in the corresponding open interval ab. And the third property is that f of a should be is equal to f of b. These are the three properties that has to be satisfied by this function f. And in all the theorems, mostly you will find that this function f would satisfy these two criteria. Hmm? This first and second kind of criteria would be common. and some changes would be there in the third criteria, and for different change in this third criteria we will have different theorems. So at first in this Rolle's theorem, we are having all these three criteria. The first criteria is that f should be continuous in the closed interval ab, and its derivative exists. That means f dash exists in the open interval ab. And the third criteria is that f of a is equal to f of b. Now, if these three conditions are satisfied, got it? If these three conditions are satisfied by the function f, then we are going to show that there exists at least one number c where a less than c less than b, such that f dash c is equal to 0. Okay, there exists at least one number c where a less than c less than b, such that f dash c is equal to 0. That means f dash derivative f dash c, generally what we mean is that f dash means generally, let me show you in a different way. uh, Generally f dash, suppose over here we know that f dash means, suppose y is equal to fx. hmm. Y is equal to fx, and then f dash means dy dx. That is actually f dash x. Hmm. And if we try to find out the value of dy dx at the point c, at the point, suppose x is equal to c, in that case this should be written as f dash c. And the theorem says, the statement of this theorem says that this f dash c should be is equal to 0. That means this dy dx should be is equal to 0 at the point c. We know what is dy dx, that dy dx always represents the gradient of the tangent. Gradient of the tangent of the curve of the function fx. fx ফাংশনের যে কার্ভ থাকবে তার গ্রেডিয়েন্টটাকে কার্ভ থাকবে তার ট্যানজেন্টের গ্রেডিয়েন্টকে রিপ্রেজেন্ট করছে dy dx. So dy dx represents the gradient of the tangent of the curve of represented by the function fx. And this gradient, if this gradient becomes is equal to 0, then the corresponding tangent must be parallel to x-axis. Is it okay to you, everybody? ব্যাপারটা ক্লিয়ার, বুঝা যাচ্ছে?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay, thank you. So we can say that this statement geometrically, what would be the geometric meaning of that statement? That means under these three criteria, the theorem says that there must be at least one point c where a less than c less than b. That means c must be an interior point in this interval ab. Okay, it is not equal to the boundary point a, nor is it equal to the boundary point b. So apart from these two boundary points, c would be an interior point. That's why strict inequality appears over here. C is an interior point, and minimum one such interior point must be there at which derivative becomes is equal to 0. That means the tangent to this curve becomes is equal to 0. Got it? The tangent to this curve is not equal to 0. Actually, we should say in this fashion that the tangent to this curve becomes parallel to x-axis. The gradient is equal to 0 means the tangent to this curve becomes parallel to x-axis. You got my point? So the curve should look like this. Let me draw something, whether it is possible or not. Let me draw it in this way. Just a minute. I don't know whether it would work or not. Yeah. Suppose we have a curve, this kind of curve. These are the coordinate axis, and this is, suppose this is the curve of this function, say fx, and the function is continuous. Over here it is written that the function is continuous in the interval ab, therefore we don't have any break in this function at all. And suppose this is the number a and this is the number b. Okay, this is the endpoint a and this is the second endpoint b. And what about this derivative? And this derivative f dash exists. F dash exists means at each and every point in the open interval ab, not at this left end point, nor at this right end point. Not, I don't know what color should be suitable over here. Yes, it is visible. Not the left end point nor at the right end point the function is differentiable, but within the open interval, within the open interval the function is differentiable. That means apart from the points a and b, we can always draw tangents like this in each and every point. Got it? And the third criteria says that f of a should be is equal to f of b. That means this height, this is the height f of a and this is the height f of b. These two heights must be same. This is the third criteria, f of a is equal to f of b. Got it? And the first final conclusion says that f dash c is equal to 0 means minimum one point is there, at least one point is there at which the tangent would be parallel to x-axis. Over here this is the point. Now over here if we want to draw a tangent, hopefully this would be parallel to x-axis and corresponding point would be this point. This would be the point position of the point C. Got it? And similar case may arise at this point, at this kind of point, at this kind of point, and at this kind of points. That's why the possible position of C may be this one, and possible position of C may be this one. The possible position of C may be this one as well. Okay, so that's why the theorem says that at least one number C is there such that f dash C becomes is equal to 0. This is a geometric interpretation of Rolle's theorem. So now we can say that under these three conditions, the derivative becomes is equal to 0 at certain intermediate point. It means that geometrically the tangent must be parallel to x-axis at least minimum at one point where a less than c less than b. Now did you got the geometric interpretation? Is it clear? ব্যাপারটা তোমাদের কাছে ক্লিয়ার হলো জিওমেট্রিক ইন্টারপ্রিটেশনটা?
Yes sir.
কারো কোনো কোশ্চেন আছে?
Yes,
ডু ইউ
sir.
হ্যাভ এনি কোশ্চেন?
স্যার যদি এই তিনটা ক্রাইটেরিয়া যদি স্যাটিসফাইড হয় তাহলে f dash c equals to 0 হবে। যদি এই তিনটা ক্রাইটেরিয়ার মধ্যে কোনোটা যদি স্যাটিসফাইড না হয় তাহলে কি f dash c equals to 0 কোনো কার্ভের ক্ষেত্রে হতে পারে?
হতেও পারে, নাও হতে পারে, গ্যারান্টি নেই। রোলস থিওরেম বলছে তিনটা কন্ডিশন স্যাটিসফাইড হলে f dash c is equal to 0 হবে, that is guaranteed. We are going to prove that result. But if these three conditions are not satisfied, then we don't have any guarantee that f dash c becomes is equal to 0 or not. It might be equal to 0, it might not be equal to 0. Okay. Any other question? No, nothing. So let me go to the proof. Generally in your exam along with proof the question about this geometric interpretation comes along with that proof.
Question আছে?
Yes sir, follow.
আমি যদি সার্কেলের ক্ষেত্রে তো মানে f ড্যাশ সিটা আমি 0 পাবো কিন্তু রোলস থিওরেমের ওই যে ক্লোজ ইন্টারভ্যালটা ওটা পাবো না।
কি বললে বুঝলাম না? সার্কেলের ক্ষেত্রে
আমি সার্কেলের ক্ষেত্রে তো a is equals to b হয়ে যাচ্ছে না? যদি আমি a মানে যে পয়েন্ট থেকে স্টার্ট করব সেই পয়েন্টেই তো আমার সার্কেলটা আসবে ঘুরে।
আচ্ছা, সার্কেলের ক্ষেত্রে সিচুয়েশনটা একটু আলাদা হবে। ইন কেস অফ সার্কেল তোমরা ওরকম ভাবে অ্যাজ সাচ কোনো ফাংশন পাবে না। কেন ফাংশনটা পাবে না? আমি একটা পিকচার ড্র করার চেষ্টা করছি এখানে। সাপোজ এখানে ড্র করি এই পজিশনে। সে ইন কেস অফ সার্কেল, this upper portion would be one function and this lower portion would be another function. এই যে লোয়ার পোর্শনটা ড্র করছি, কেন এরকম সিচুয়েশন তৈরি হচ্ছে আমি এই যে এখানে রাফ একটা পোর্শনে দেখাই, এর মধ্যে আর ডিটেল কিছু করছি না, রাফ ওয়ার্ক একটু দেখাই। বিকজ ইন কেস অফ সার্কেল, the equation of the circle is x square plus y square is equal to suppose a square. Okay, a না বলে আমি এখানে r square বলে দিই বোঝাতে সুবিধা হয়, বিকজ a b ইউজ করা হচ্ছে। নাও দিস ক্যান বি রিটেন অ্যাজ y is equal to plus minus root over of r is actually constant quantity r square minus x square. This is the equation of the circle. Okay, now generally the definition of function, তোমরা যদি ফাংশনের ডেফিনেশন তোমরা কনসিডার করো, definition of function says that for each value of x we would get one and only one value of y. That is the definition of function. ফাংশনের ডেফিনেশনে বলা হয়েছে, তোমরা ওই যে সেট থিওরি যখন পড়া হয়েছিল, relations and then functions, in the definition of function it says that for each value of x we will get only one value of y. But over here if you put any value of x, suppose x is equal to, তোমরা যদি 1 put করো or 0, even if you put x is equal to 0, you will get plus and minus two values of y. Okay, so plus, for plus portion, that means if you consider this simply this portion, this kind of expression, y is equal to this kind of expression, that is a function, and similarly y is equal to minus of this expression, that would be another function. The positive part is actually represented by this kind of upper segment, and this negative portion, due to this negative portion, this second curve actually represents this lower portion. So in case of circle, if we just consider this equation, this equation actually represents two different functions together. This kind of functions are actually called implicit functions. Ordinary function না, এই টাইপের ফাংশন গুলোকে বলা হয় explicit function. This kind of functions are called explicit functions, and this kind of functions are called implicit functions. We will discuss in detail about explicit and implicit function in the chapter of functions of several variables. দেরি আছে এটা অনেক। For the time being, at least we can say that in case of functions only, if you consider the circle, then either you will have to consider the upper portion and the or the lower portion, any one, যে কোনো একটা কনসিডার করতে হবে for to match this result. এই রেজাল্টটা ম্যাচ করার জন্য আমাদের যে কোনো একটা পোর্শন আমাদের কনসিডার করতে হবে। Now suppose you consider this upper portion, then forget about this lower portion. Now in this upper portion, if we draw this kind of two coordinate axis, suppose these are the two coordinate axis, then this much height is equal to f of a, this much height would be is equal to f of b. Clear? এই দুটো হাইট সমান হবে। আমার পিকচারটা হয়তো একটু আলাদা হতে পারে, আমার এখানে একটু ড্র করতে প্রবলেম হচ্ছে, বাট দিস মাচ হাইট would be is equal to f of a, and this much height একটু আলাদা করে ড্র করলাম, this much height would be is equal to f of b. And now this parallel tangent parallel to x-axis would be this kind of tangent. Got your answer?
Yes sir.
আর কোনো কোশ্চেন আছে?
Yes, sir.
আর কোনো কোশ্চেন আছে? তাহলে আমি কন্টিনিউ করছি। এই যে এই পিকচারটা কিন্তু মুছে দিলাম, এরপরে ড্র করতে পারবো না। এই পিকচারটা মুছে দিচ্ছি। যদি ফার্দার আবার কোনো কোশ্চেন থাকে তাহলে তোমাদের এই ভিডিও রেকর্ডিংটা ইউটিউবে দেওয়া থাকবে, তোমরা একটু দেখে নিতে পারো। আমি এটা মুছে দিলাম। ওকে, so now let's continue. So let's move to the mathematical proof of this theorem, the Rolle's theorem. And in this proof, we need results of continuous functions. That I already posted all these results, everything in YouTube earlier. ওই দুটো চ্যাপ্টার থেকে যে রেজাল্টগুলো আছে সেগুলো আমাদের এখানে দরকার পড়বে। So we are given that the function f is continuous function defined on the closed interval ab, and we know that a continuous function defined on a closed interval is a bounded function. One standard well-known theorem in the chapter of continuity is there. It says that a continuous function defined on a closed interval ab is a bounded function. Therefore, we can say that f must be bounded over the interval ab. Of course, on the interval ab, f is a bounded function. That means the upper supremum of the function f on the interval ab, and the infimum of the function f over this interval ab. Both of these two must exist. Okay. Now, and one more result is there that says that at least 2 points are there. One is alpha and another is beta, such that this supremum value m becomes is equal to f of alpha, and this infimum value small m would become is equal to f of beta. Okay. Now we are going to show that at this point alpha or maybe beta, anyone at alpha or at beta, the tangent is parallel to x-axis. That means the derivative at the point alpha or at the point beta becomes is equal to 0. That means c is equal to the point alpha, or you can consider c is equal to the point beta. But in that case, we will have to ensure that alpha and beta must belong to the corresponding open interval, because in the statement it says that a less than c less than b. If by chance we have to prove that c is equal to alpha, in that case you have to first prove that alpha is a point where a is strictly less than alpha and alpha is strictly less than b. So target এরকম থাকবে that c is equal to alpha or c is equal to beta. That would be our target. কেন? The question is why? কেন আমি এরকম ভাবে বলছি? Let me draw the picture again. Just simplified version of this picture. Say this kind of curve is there. This is the f of a, and this is the height f of b, and suppose this is the point, this is the maximum point, this is the point at which we achieve the maximum value, and say this is the point, suppose the point alpha. Okay, and this is the height capital M. This much height is equal to our capital M, the supremum of this. Okay, then we know that at the extreme values, at the point of maximum and minimum, if the function is differentiable, then the corresponding derivative dy dx becomes is equal to 0, or the tangent is parallel to x-axis, and that we need to prove. আমাদের তো এরকমই কিছু একটা প্রুফ করতে বলেছে। Clear? So alpha is a possible candidate যেখানে ম্যাক্সিমাম বা মিনিমাম অ্যারাইজ করবে, সুপ্রিমাম এখানে অ্যারাইজ করছে, সুপ্রিমাম ইজ দ্য লার্জেস্ট ভ্যালু। সো আলফা would be a possible candidate for becoming equal to the number c. ব্যাপারটা বোঝা গেল? Alpha is a possible candidate which can be equal to c. Is it clear to you? বোঝা যাচ্ছে ব্যাপারটা? Why alpha? Clear? Similarly, beta is also a possible candidate, because beta point curve should look like this at the point beta, and minimum value at minimum value the tangent should be parallel to x-axis. So this is possible. So that's why these are all motivation Mathematically this may look a little bit odd, but if you consider the geometry, the idea becomes clear. So our target is to show, we are going to show that C is equal to alpha. We are just arbitrarily considering our target as the point alpha. And one simple case may be there that capital M maybe is equal to small m. Suppose if the function f is a constant function. If f is a constant function, we know that constant function is always a continuous function, and we can always differentiate a constant function. We get the derivative is equal to 0. And for that constant function, this derivative becomes equal to 0. Therefore, at each and every point in between a and b, this derivative becomes is equal to 0. All the points in between a and b satisfy the final conclusion. F dash c is equal to 0. So that is an obvious case. If capital M becomes is equal to small m, then the function would be a constant function, and the result is obviously proved. So this is one case, the simplest case that may arise. But the other case where m is not equal to capital M is not equal to small m, that means supremum is not equal to infimum. For that case also we will have to prove the result. So we are going to prove the result for this second case, and in such cases let me draw the picture again, because I need to explain many things over here. Suppose this is the coordinate axis, and say this is the curve. This much height. This is f of a. This is f of b. Now f of a, over here it may appear that this is the maximum value. This is the height capital M, but this is the point alpha. Okay, so it may say you will find that this capital M, this height capital M, is not equal to this height. What is this height? This height is actually equal to f of a. And capital M in that case, as because f of a, this height is equal to this height. If capital M is not equal to f of a, then capital M would not be equal to this f of b as well. So we can say that f of a is not equal to m, or f of a is similarly we can say that over here, suppose this is the minimum value, might be the curve would look like this. Say this might be a different kind of curve. Say this curve may look like this. And in that case, say this is the value small m, the minimum value of the function. So over here, this much height is equal to small m. So this height small m is not equal to f of a, and this height small m is not equal to f of b. So at least we can say over here m is not equal to f of a, and small m is not equal to f of a. Okay, either m is not equal to f of a or small m is not equal to f of a. These two cases may arise. Now let me make it a little more clear. Over here you see, if suppose f of a becomes is equal to capital M, then we can definitely say that f of a is not equal to small m. And if by chance f of a becomes is equal to small m, then definitely we can say that f of a is not equal to capital M. And in other cases, the third case may arise that small m less than f of a, and that is less than capital M. And in that case, we can say that f of a is not equal to small m, as well as f of a is not equal to capital M. Okay, that's why we can say that either f of a is not equal to m, or f of a is not equal to small m, or both these results are true. Is it clear? এই পোর্শনটা ক্লিয়ার হলো সবার কাছে?
Yes, sir.
কোনো কনফিউশন নেই তো? বিকজ এটা
Yes,
কিন্তু
sir.
ফান্ডামেন্টাল পার্ট। So hopefully clear. Now, so possible two subcases may be there. F of a is not equal to m, or f of a is not equal to small m. If f of a is not equal to m and m is equal to f of alpha, আমরা আগে অলরেডি কনসিডার করেছি that m is equal to f of alpha. So f of a is not equal to m and m is equal to f of alpha. Therefore আমরা বলতে পারবো that as because f of a is as because f of a and f of b are same, these two endpoints, this height f of a and this height f of b, these two heights f of a and f of b, as because these two heights are same and f of a is not equal to f of alpha, therefore f of b should also be not equal to f of alpha, since f of a is equal to f of b. Got it? And from this result over here, f of a not equal to f of alpha means that alpha is not equal to a, because if by chance alpha becomes is equal to a, in that case f of alpha and f of a must be equal. Similarly, f of alpha is not equal to f of b implies that alpha is not equal to b. That means we already know that alpha is a point in between this closed interval a and b, but over here we have proved that alpha is not equal to a and alpha is not equal to b. Therefore we can say that a less than alpha, strictly less than b. That means alpha is a point that is actually an interior point, not the boundary points a and b. Okay, so the first part that we need to prove in this theorem, that our target is to show that c is equal to alpha. So we have successfully proved that the candidate for c, that is actually alpha, it satisfies the condition that a less than alpha less than b. So this much portion proof is complete. Okay. Okay, now so we have proved that a less than alpha less than b. Now we are going to prove that f dash a alpha is equal to 0, because we know that at the extreme points or at the maximum or minimum points the derivative becomes is equal to 0, provided that derivative exists. Over here we are given that the derivative exists in the open interval. So it should be f of alpha. Now we have to prove that f of alpha is equal to 0. How to prove this one? Over here, f of alpha is equal to m, that is the supremum. Supremum means least upper bound. So it is an upper bound, least of all the upper bounds, that is called the supremum. So it is an upper bound, and from the definition of upper bound we know that f of t is less than equal to capital M, or f of t is less than is equal to f of alpha for all t belonging to the closed interval ab. And what is alpha? Alpha is an interior point. That means alpha is not equal to a and alpha is not equal to b. So some gap must be there in between this left boundary a and the point alpha, and some gap should also be there in between this alpha and the right boundary b. And we are utilizing the gap. We are choosing a sufficiently small number h so that this a plus h falls within this gap. That means if h is positive, then a plus h should lie within this gap, and if h is negative, in that case a plus h would lie within this gap, so that we can say that a plus h belongs to the interval a comma b. Clear? Kono question ache so far? Does
No, sir.
anybody have any question? No question. Okay, so hopefully it is so far so good. Let's continue. Now, in this equation number 1, if we put t is equal to this number alpha plus h, because this equation is true for all point t belonging to the interval ab, and over here alpha plus h is a point in the interval ab, so we can put t is equal to alpha plus h in equation number 1. And if we put t is equal to alpha plus h in equation number 1, we will have f of alpha plus h is less than is equal to f of alpha. So far, we have not imposed any restriction that h is positive or negative. H may be positive, h may be negative. Now we consider two cases when h is positive and when h is negative. If h is positive, okay, we can take it on the left hand side. Suppose if f of alpha is taken on the left, we will have f of alpha minus f of alpha plus h minus f of alpha, that is less than is equal to 0. This numerator would be less than is equal to 0, and if h is positive, then dividing this inequality by a positive number will keep the inequality as less than is equal to inequality. If h is negative, then this less than is equal to inequality will be converted into greater than is equal to inequality. We are not considering the case for the time being, at least. Over here, h is greater than 0. So whenever we divide this expression by a positive quantity h, this less than inequality will remain be a less than inequality. Okay. And now we take the limit as h tending to 0 from right hand side, because h is positive. So h tending to 0 plus. We are taking the limit h tending to 0 plus. Got it? And what is this limit? We know that the derivative of the function at the point alpha exists because alpha is an interior point. We are given that the derivative exists in the interior points. Therefore, we can say that this derivative must be is equal to the right derivative, and right and left derivative both must exist because of the fact that f dash alpha exists. So right derivative and left derivative must be is equal to f dash alpha, and therefore this right derivative exists, and we can now put in place of f dash alpha plus 0, we can simply put f dash alpha. So what we obtain? We obtain that this in place of f dash alpha plus h, we are putting f dash alpha that is less than is equal to 0. We got one result. It says that f dash alpha is equal to 0 if h is positive. Now again, we take h as a negative quantity. For the next part, we take h as the negative quantity, and therefore this numerator was initially less than is equal to 0 from this inequality. But if h becomes a negative quantity and we divide this numerator by this h, in that case this less than is equal to sign will be converted into greater than is equal to sign. That's why I have written greater than is equal to over here, because of the fact that h is a negative quantity and this numerator or the entire inequality has been divided by h. Therefore, this expression would be converted into greater than is equal to inequality. Okay. And now we take the limit as h tending to 0 minus. We take the limit as h tending to 0 minus. So we ultimately get this kind of limit. And why 0 minus? Because h was taken as a negative one. We ultimately got this kind of limit, and this limit would be is equal to the left derivative, and as because this left derivative becomes is equal to f dash alpha, therefore in place of left derivative we can say that f dash alpha is greater than is equal to 0. Okay, so we get two different results. One is this equation number 5, another is this equation number 6. In both of these two equations are satisfied. F dash alpha is less than is equal to 0, and f dash alpha is greater than is equal to 0. Got it? Both of these two results can be satisfied together only when this f dash alpha is equal to 0. Again, I am saying that both of these two equations can be satisfied only when f dash alpha becomes is equal to 0. So the only possible conclusion that we can draw is that f dash alpha is equal to 0, and we have already proved that a less than alpha less than b. So this is the proof of the result here. Over here in case of c, we can say c is equal to alpha. We got the result proved for the point c is equal to alpha. So minimum one point is there, more than one point might be there, we don't need to prove that one, just আমাদেরকে prove করতে বলা হয়েছে just minimum one point, at minimum at one point we will have to prove the conclusion of this theorem. So we can say that the theorem is proved. Now is it clear to you? সবার কাছে clear? Do you have any question থাকলে জিজ্ঞাসা করতে পারো। কোনো কোশ্চেন নেই?
No, sir.
No, sir.
Okay, so this is the original form of mean value theorem. This is the original form of Rolle's theorem, not mean value theorem. Okay, and we have two more versions of the same theorem. One is called the h-theta form. What is h-theta form? Just nothing. In place of b, we put a plus h. So this h over here, this h would be different from the h that I considered. Okay, in the previous proof, h was a sufficiently small number so that alpha plus h belongs to the interval ab. So don't mix this one with this second statement. Okay, second version of the proof. Just over here, what is h? We can say h, a plus h is equal to b. Then what we can say? We can say that over here in this second portion, we can say that b is equal to a plus h. Over here, we can say that b is equal to a plus h. We can say like this: b is equal to a plus h. And if b is equal to a plus h, in that case b minus a would be is equal to h, and over here h is always positive, mind it. B becomes is equal to a plus h, so that b minus a becomes is equal to h. And what was the point? Alpha was a point that was lying in between a and this number b. B is equal to a plus h. So if we subtract the number small a throughout this inequality, we will have 0 less than alpha minus a less than h, and h is a positive number. Therefore we can say that if we divide the entire inequality by the positive number h, this less than inequality and this less than inequality, both of these two less than inequality will remain be less than inequality. And ultimately we will have on the left hand side we will have 0, on the right hand side dividing by h we will have 1, and this middle term would be alpha minus a divided by h, alpha minus a divided by h, and let us call it theta. So we can say that 0 less than theta less than 1, and in such cases if alpha is equal to if alpha minus a divided by h is equal to theta, in that case alpha is equal to, we can write it as a plus theta h. Okay, and therefore we can rewrite the statement in terms of, everything should be written in terms of h and theta. Forget about b, everything should be written in terms of h and theta. Initially what we had in the original version of the theorem, we had the fact that f is a continuous function. We had f was a continuous function. So now the statement should be written as f is a continuous function, fine, but the interval should be a comma a plus h. We had the result that f dash exists in a comma b. So now we have to write f dash exists in a comma a plus h. And thirdly, f of a is equal to f of b. So this should be f of a is equal to f of a plus h. And finally, we had the result that there exists at least one number C. Now corresponding to this number C, you see over here, corresponding to the small quantity alpha or C, whatever you write, we can say that for each value of theta, we get one value of the point C or alpha. Over here C is equal to alpha. Therefore, we can say for corresponding to each value of C, we get each value of theta. So over here, if this is the points, one point say theta is equal to theta 1, this is a possible another point say theta is equal to theta 2, and that similarly one such point would be there in this position, maybe theta is equal to theta 3, where the tangents becomes parallel to the x-axis. Got it? That's why we say the statement is written in this way: there exists at least one number theta where 0 less than theta less than 1, such that f dash c is equal to 0. C means a plus theta h. Got it? So f dash a plus theta h would be is equal to 0, and that would be, this would be the h theta form of Rolle's theorem. ব্যাপারটা clear হলো? h theta form the statement. Is it clear to you?
Yes, sir.
Yes, sir.
Now I am keeping a homework for you, that you please make the proof of the Rolle's theorem in h theta form ready for yourself. I am not going to give you any material. This is not available in any other books as well. In most of the books, this statement is there. So you will, and this proof of the original statement is there. So just keep this statement in your mind. You can consult the book, and then parallel to this proof, you try to make the proof of this h theta form of Rolle's theorem, because in exams sometimes the h theta form is directly mentioned in exam, and in that case you will have to ultimately write everything in terms of a and h and theta. Got it? So you don't need to use the original version. So you will have to be ready for the exam. I would suggest you to write this kind of extra proofs in loose sheets, and after completing these proofs you keep it in a file, so that it would become a note, ready-made note by you for your exam. Before the exam you don't need to search other books. That is my advice. Got it? So I am keeping this result for as a homework for you. Okay? And I don't know where some noise is there. I don't know from where did you get this one. Anyway. And I am keeping one more result as a homework, that is called the Maclaurin's form of Rolle's theorem. What is this? In Maclaurin's form of Rolle's theorem, the interval is taken as 0, x. In place of a and a plus h, if you put a is equal to 0, then the interval becomes 0, h. And in that case, if you put h is equal to x over here, you will get the interval 0, x. Okay, and x would be a constant quantity, not the variable. That's why in this proof I have taken the quantity small t as a variable, not the quantity x, so that x can be used later on as a constant quantity. Got it? I am total in this throughout the proof I am taking this variable as the quantity t, not the variable x. That's why now we can use this quantity x as a constant quantity, the right boundary. Okay, and the statement would be the fact that f is continuous in the closed interval 0, x. Its derivative should exist in the open interval 0, x, and f of 0 would be is equal to f of x. Then there exists at least one number theta where 0 less than theta less than 1, such that f dash a plus theta into h. In place of h we are writing x, in place of a we have to write 0. So a0 plus theta x would be equal to simply f dash theta x. Okay, therefore the final conclusion is that f dash theta x is equal to 0. And that is the Rolle's theorem in Maclaurin's form. Maclaurin's form, this version. Try to be very careful about this spelling. Maclaurin is a mathematician. And this form of Rolle's theorem is called Maclaurin's form, and then this last portion, this Maclaurin's form would be the most useful part for solving problems on Rolle's theorem. Got it? In exams, at least, if you are given any problem, mostly we use this Maclaurin's form. And if the statement in Maclaurin's form are directly given in your exam, so you'll have to write the statement directly. You'll have to write the proof of that theorem. So I would rather suggest you to please make make the proof ready for yourself. And keep it in a file, so that ultimately it would become a ready-made note before your exam. So I think today I should stop now. If you have any other question related to this portion or related to any previous part, you can ask.
স্যার সুপ্রিমাম আর ইনফিমাম ছাড়াও তো আমি এফ ড্যাশ জিরো পাইতে পারি।
হ্যাঁ, পেতে পারি। কিন্তু সেখানে ওই ম্যাক্সিমাম পাওয়া যাবে। আমাদের এখানে মিনিমাম একটা পয়েন্ট কোথায় গেল? ছবিটাই তো মনে আউট করে দিলাম। মিনিমাম একটা পয়েন্ট সেখানে, দাঁড়াও দেখি ছবিটা আবার এখানে আসবে কিনা আমি জানি না। মিনিমাম একটা পয়েন্টে আমাদেরকে এখানে ডেরিভেটিভটা 0 দেখানো দরকার ছিল। সো আমরা আপাতত ফর দ্য সেক অফ কমপ্লিট প্রুফ অফ দিস থিওরেম আমরা একটা মিনিমাম পয়েন্ট কনসিডার করলাম, যে পয়েন্টে এই থিওরেমের প্রুফটা আলটিমেটলি হোল্ড করছে, এবং সেখানে আলটিমেটলি সাকসেসফুলি আমি দেখাতে পারলাম এফ ড্যাশ আলফা বিকামস ইজ ইকুয়াল টু 0। বাট আরো বিভিন্ন পয়েন্ট থাকতেই পারে ম্যাক্সিমাম, সুপ্রিমাম বা ইনফিমাম ছাড়া, যে পয়েন্টগুলোতে ফাংশনের ডেরিভেটিভ 0 হতে পারে। সেই জন্যই তো বলা হচ্ছে মিনিমাম 1 পয়েন্ট। মিনিমাম বলা হচ্ছে, ম্যাক্সিমাম তো বলা হয়নি। 2টো 4টা 10টা 15টা পয়েন্টও থাকতে পারে এরকম, তাই না?
ইয়েস স্যার।
And any other question? Okay, so এটুকুই আজকে তাহলে থাকুক।